Hello and welcome. But now, let's begin with the Docker course. The aim of this course, and specifically this chapter, is to answer what exactly is a container and how can we use it efficiently. We will use practical examples to explain this as clearly as possible, and then we will see how Docker fits into this. Let's get started. Basically, a container is composed of namespaces. This is a method provided by the kernel to isolate parts of the system or reduce visibility of those namespaces from the rest of the system. These namespaces work like a tree, and I found this diagram to be quite simple to understand, so let's check it out. It's made up of several layers or different parts of the system that isolate different things. Then the API we will work with through several tools invokes basically Syscalls or system calls. Those tell the kernel what we want to do with any given namespace. In the documentation you can find more information and detail about how it works. It's very clearly explained, so I recommend checking it out if you are interested. But for now, we will go over some of the namespaces we will be using. Among them, we have PID, which isolates the process tree, meaning that our container will have its own process tree, with the primary process having the PID 1. Mount isolates the file system. Network namespace will isolate routing tables, interfaces, firewall rules, and a few more things. The user namespace will isolate user IDs and group IDs. We won't be using this one much right now, but it's good to know about it. IPC isolates the POSIX message queues and shared memory systems. Then we have UTS, which is basically for the hostname. So each container can have its own hostname without affecting the host. Then we have cgroups, which are a bit different because instead of isolating things, they limit resource usage like CPU, memory, and a bunch of more things that we will see later on. Then we have the time namespace. This one isolates the system time, so different namespaces can have different times, which is useful for testing process in isolation. Time namespace. This isolates the system time, so different namespaces can have different times, which is useful for testing processes in isolation. So those are basically the namespaces that are available, and next we will be checking the system calls. We have clone, which basically creates a new namespace of the type that we specify. We have setNS, which basically allows us to enter an existing namespace. With unshare, depending on the flags, we can either create a namespace or join an existing one. And IOCTL is used to retrieve information about the namespaces. That's a simplified overview of namespace and system calls. We don't need to dive deeper into this right now, but later on in the security section, these topics will probably come up again, so it's useful to mention them now to keep them in mind and start understanding how Linux isolates containers under the hood. Each process has a directory within /proc, the PID, /ns. That folder basically will tell you all the namespaces for a given process and at any given time. This gives us an idea of how a container will look if we were to create, for example, a container with all the namespaces, for example. So This is approximately what a container will look like, assuming we created all the necessary namespaces. This is about what we will be doing manually and then with Docker. We can see it as layers, which is kind of how it works under the hood. It's interesting to see and understand that they work as different layers and they don't depend much on one another. So having that overview, we can see that a namespace is essentially a layer of abstraction for each part of the system. But how do namespaces work? By definition, a process can only belong to one namespace of each type at a given time. Once a namespace is created, the process operates in this new environment, independent from the rest. Now we will do a small exercise by running some command to verify how unshare can create a PID namespace and remount /proc to have its own process tree. As you can see, our bash shell should have the PID number 1, and we cannot see the processes from the host, which is what we were expecting. Next, we will compare the namespaces of our container against the host, and we should only see differences in PID and MNT, which is basically what we cloned. There are several reasons to use namespaces or containers. Some of them could be to isolate a process or running applications in multi-tenant environments, to test things without affecting the host. For example, you need a container using a different time zone, for security, or to make the best use of available resources. These are just a few examples. I'm sure there are plenty more. There's always the comparison between containers and virtual machines. Are they the same? The short answer is no. The main difference is that containers share the host kernel and system resources in a more lightweight manner. Security and isolation are weaker compared to virtual machines. Containers have near instant startup times, while virtual machines take longer since they need to emulate all the system's devices. Containers are more portable, lightweight, easy to distribute, and behave the same way on any host that supports them. Virtual machines, on the other hand, take longer to start because they need to emulate all devices, have their own complete operating system, have more overhead, and in general require more configuration. As we can see in this image from Atlassian, we can see that virtual machine, each machine has its own operating system with its own kernel, while the containers only have the application binaries, the required libraries, and they interact with the kernel through the container engine. Okay, so far so good, but let's take a look at what came before Docker and perhaps a bit what might come after. Before Docker there were weaker containers, technologies or semi-virtual machines. Some examples are OpenVC and LXC, which stands for Linux Container. Docker became popular because of its simplicity and the standard it proposed, making it easy to reproduce and distribute containers. There were other popular alternatives for Docker, but those are the ones I remember using. In the future, you will hear a lot about micro-VMs and unikernels. They have some differences in how they function and their use cases. Micro-VMs, like Firecracker from Amazon, are for example used to run Lambda functions. They offer external isolation, speed, and function almost like virtual machines. One interesting detail about Firecracker or micro VMs is that you can essentially convert a container into a virtual machine. This is what fly.io does to run your containers. Now onto the practical part. First, we need to install several tools to work with routing tables, iptables, bridge, and cgroup. Before we begin, let's go over the example we will be working on. We're going to create two isolated environments to simulate a common scenario. We will call them app and db. App will be able to connect to the internet, and db will only be able to communicate with app. We'll see how to turn our host into a router to give internet access to our container on Namespace. To make that work, we're going to create two pairs of virtual interfaces called bet, which we will connect to the containers and the bridge. Imagine when you create a virtual bet pair, it's like a cable and each end connects to a container or a bridge. But first, let's check if the bridge is already created. If not, you can create one with the commands shown in the screen. Next, we create the namespace for app and db. I will list them just to verify. So far, so good. The next step is to create the pair of virtual interfaces for app and db. If we list the interface type, we will see 4 ends of our virtual interfaces with the names we specified in the previous command. Now we'll connect those virtual interfaces to the appropriate ends. First for app, we connect it to the namespace and the other end to the bridge. We will do the same for db. After that is done, we will need to assign some IP addresses to them. Make sure to copy the right IPs, and then we can verify if the interfaces exist and are assigned to the containers and they have the right IP addresses. Everything looks good. So the next step is to bring up those interfaces in both ends, both for app and for db. Once that is done, we can do a connectivity check, basically to make sure our network is running as we expect. As we can see, our virtual interfaces are on the bridge, so everything looks good. So we are ready to test connectivity, and we see that it works both ways, which is great, exactly what we were expecting. Now we're going to test outside world, let's say, communication, and that obviously will fail because we don't have a root. We can verify that with IP root, and for this to work we will need to add default root in our container and turn our machine or host into a router. We need the masquerade rule for NAT and the default root pointing to our bridge to be able to use it as a gateway. As we can see, now we can reach Google DNS, so we have internet basically in our namespace. Now we are going to create a cgroup. Cgroups can be manipulated with just basic Linux commands, like you can see with mkdir we were able to create a cgroup, and the kernel took care of the rest. Now we will apply certain limits. Those limits will be 25% CPU and 50 megabytes of memory. To make this Pretty easy, we pick those low limits. We will run a few comments after applying the C groups, and we will verify that the CPU limit is being enforced. One thing to note is that tasks won't be killed by CPU usage in this scenario, but as you can see, the time will grow, meaning that processing will be slower. We can also use systemd cgtop to monitor C groups, which is pretty handy. As we see, the CPU cannot go over 25%, which is what we expect. Now we will test memory usage, and what will happen here is our Python process will be killed by the OOM killer. Basically because we will be using way more memory, or trying to use way more memory than what we have allowed. This can be adjusted, but in this example it won't, so the process will just be brutally killed by the OOM killer. This can be verified using the demystify command in the host. So we can also check using cgtop, and we can better see that we never exceeded the limit and our process still got killed. Next, we will create a more realistic example. This will be the closest that we will be to a Docker-like container. Basically, we will copy all libraries and some binaries that we want to run, mimicking common Linux file system. What we will do here is tie everything together and try to have a container as the image that we shown at the beginning. We will use a really long command that we will see shortly, but for now we will need to copy everything, mount the right directories, deb, proc and sys, and then recreate the C group with cgcreate and set the limits with cgset. Once we have that in place, we can see that we have everything isolated in our let's call it container. So basically this big command, what it does is with cgcreate, cgexec we call the netns exec command, which then calls unshare, which then does chroot, which then remounts proc, and finally invokes our shell. It's a bit more detailed in the text if you want to pause and maybe read it, if that makes sense. But as you can see in the container, we have our own process tree, we have user IDs isolated as well, and we are in a chroot, so we are basically in our own environment at the moment. This was mostly inspired by Docker, which is basically Docker in 100 lines of bash. And I think it's great to learn how things like Docker work underneath. We will test changing the hostname and checking also in the host. We can see that it doesn't affect the host. The container has its own hostname now. We can also check that the namespace still have its IP and the network configuration, and we will test again limits, CPU and memory. Everything seems to be working fine for the CPU, and everything seems to be still working fine for the memory limit. That was a lot of work to have a container. We could have a script for this, but it will be probably impractical and error prone. As I said, this was inspired by Docker, and I think it's great for learning how things work. Here we can also see the mesh and how it tells us from the kernel why a process got killed and which C groups were playing there. Now that we have seen all that, we have a better understanding of how Docker works, and we can view it differently. This will also help us understand the functionalities, limitations, and security aspects. But wait, this is not over yet. Let's check how Docker works. I recommend checking the instructions for your specific distribution directly from the Docker website, because it's well documented and probably the most effective way to install it in your distribution. In my case, I already have installed Docker. I have here the instructions for Ubuntu. With those comments below, we can add our user to the Docker group, so we can run Docker without using sudo. And then with a new group, we can refresh groups for that terminal without needing to log out or reboot the machine. Remember to run that if you open a new terminal before rebooting. Now let's check our first Docker file. It's pretty simple. First we tell it what base image to use with from. Python provides us with a base image that's based on Debian, in this case because of the Slim name. Then we create a user and tell Docker that we want to run our application under this user. We specify the folder where we want our application to run, and then we copy the application over. Finally, with cmd, we execute the application. With -u, we ensure that the output is sent immediately to the screen, or stdout without buffering. We can see more details about the image in Docker Hub, and we can check each layer that makes up that image. We'll talk more about this in detail in chapter 2, covering how images are built and how they work. But for now, this is the basic knowledge you need to get things going. Next, we will look at the code. It's super simple. All it does is print app is running every 5 seconds. Lastly, let's check out the Docker Compose. Here we define our services. One is called app. With the build parameter, we tell it where our Docker file is and the name of the file. That way, Docker Compose will take care of building our image. With depends, we tell it that our application depends on DB, so DB should start first and then our application. With deploy, we set the same resource limits that we have before, and we also add an network. Otherwise, the containers will be using the default Docker bridge. In DB, as is just an example, we are using a Postgres image. We don't need to build it, just pull it. And we also specify some limits. And the interesting part here is the volume. Since DBs often times are persistent, we need a volume to keep that data safe. As you can see at the end of the file, we define a volume and a network. We will see more about those things in the next chapters. The next step is to run Docker Compose app, and with -d we will run it. We'll run our containers in the background. As you can see, first it created the network, then the volume, then started a DB, and last our application. If we check, we should see both containers running, the application as we configure, and we can also check the logs to make sure everything is working as we expected. It's printing a message every 5 seconds as we were planning. We're not going to use process for now. It's just for demonstration purposes, but it's a good example how two containers are typically created and configured and in their own network, for example. Next, we will inspect the network, and as you can see, we have our own bridge for our application. We can use the command inspect to get more details or information about the specific configuration. It's really important to get familiar with inspect because it's really useful for debugging, for example. And well, in some cases, automation, of course. Now, let's rerun some of the tests that we did earlier. But this time we will see the difference between Docker and how it will look with Docker tooling. For the CPU test, we will use the same command, and then we will use Docker stats to check our container. As we can see, the CPU still works fine. We'll use Docker exec to open another shell in the same container and test the memory limits. As you can see, it has the same behavior. The OOM killer will brutally kill our process again and again. We can check this in the demystify, and you will see it's a bit more detailed and has the same error more or less, but it's a bit more complete, let's say. Let's run another example where we launch another container. In this case, we don't have the image locally, so it will pull the image first. This container will run in interactive mode, giving us access to the bash shell. Now we can switch over to another terminal and connect this container to the network. We do this by using Docker Network Connect. We then need to specify the network and the container. Then we are going to use the command docker inspect to validate that everything looks okay and that the container is indeed in that network. We are going to look for the network settings. As we can see, in the networks we have two networks. Bridge is the default Docker network, and app is our application network, the one we created with Docker Compose. We can use JQ to filter information, and it also colorizes the output for us. So far so good. Great, so a container that wasn't part of the Docker Compose setup was easily connected to a network, but why would we need this? It could be for debugging or testing something, among other reasons. Now let's do an inspect on the network. We will remove some of the output and we will use JQ to only show us the containers. As we can see, our containers are indeed part of the network. We can see the IP address, MAC address, and more information. The last step will be to disconnect it. We use docker network disconnect to specify the network and the container, and it's gone. Now if we run inspect again, we will see that it is no longer part of the network. This is probably better handled directly through Docker Compose, even if we are adding a container temporarily for debugging purposes. But it's useful to know that everything Docker Compose does can also be done manually with Docker commands. An interesting detail is if we wanted to, we could see the network namespace with this command, and it could be useful if we wanted to investigate or debug something. Let's do one last example. In this case, we will run another container using our app image with -ti or it. We specified that we wanted it to be interactive, meaning that we will have a shell where we can type commands. With --name, we specify the name we want for the container, and with --rm, we tell Docker to automatically remove it once the container stops. If we run this, we will see that we are logged in as app user. And there is not much that we can do. We tried to use PS, but it's not there. What we will do is use lsns to inspect the namespaces of our container, call test. To do this, we first need to get the container PID. Once we have the PID, we can use this command to see what's running inside and in which namespaces. Everything looks good, as we can see. It's using all available namespaces. Next, we will use nsenter to enter our container. We could use docker attach, or if we wanted to run something in parallel, docker exec with ti. The difference is that docker attach, it will behave like a mirror since it will be the same session, while docker exec will or could execute another bash or another process in parallel. We can see that we are inside the container, and the hostname and container ID match. But did you notice that we are logged in as root? Now, I don't know if you noticed the difference, but we enter as root instead of app user by using the nsenter command. We went to use the ps command, but it's not available. But what happens if we run apt update and then apt install proc ps? It seems to work, and in our container we can see the shell, and we have PS now available. So even though our container was running as a normal user, we were able to enter as root using nsenter and modify the container. We can even see the bash shell running as root without us realizing it. Now we have the ps command available, which wasn't available before. This can be practical, but it's also dangerous. That's why it's a good practice to run containers with a read-only file system. This way, if an attacker managed to enter our container this way, they wouldn't be able to modify it. Now that we have mentioned the difference between exec and attach, let's show it just to clear any doubts. We'll use docker exec ti to enter the container with another terminal. Well, yes, it's another terminal and another shell. And as you can see, we are inside the container with app user. But what happens with attach? With attach, we do have a mirror, and it's in fact the same session. So if we exit, it will kill our container because the main PID will die, and that also kills our nsenter session. There are many security aspects to consider, but there are some specific things we should be extra careful with. For example, if we mount the Docker socket inside a container, that gives the container direct access to the host. In the security chapter, we will go over many recommendations for running containers securely and many examples like the one we just saw. We will also see other ways to run Docker without Docker, like Podman for example, and rootless containers, among other things. We have seen that using Docker for development has many benefits. It's simpler, faster, easy to share, easy to work with. This is part of why those systems have grown and developed so quickly. Finally, before we go, don't forget to clean up, and once our containers are stopped, we can see that it stopped the application and DB containers and also removed the network by app. However, if we check with Docker volume ls, we can see that our volume still exists, meaning that our data is safe. Well, I hope you like this, and here's the complete list of references and inspiration for creating this course and what's coming next. At Redbeard, we're here to help. And until next time, give us a like or leave us a comment if you enjoyed it.